we can find b pretty easily. So now we'll find b, and all we have to do is substitute. So 1 is equal to a plus b. Well, a is really 1, we said, so 1 plus b. And our x is still 3, minus 2a, which is 1, minus 3b. And so look what happens here. These 3's end up canceling out again. We'd have 3 plus 3b minus 2 minus 3b is equal to 1. And we just end up with 1 equals 1. So something went wrong here. And that something is this x equals 3 is only good for solving for a single variable at a time, because the whole point of it is to make one of these cancel. So to find b, we have to let x equal something else, and what we're going to do is let it go with, we're going to let x equal 2. Okay, so if we do that, we're going to have a 2 instead of a 3, and look what happens in this case. A is still 1. 1 is equal to 2 plus 2b minus 2 minus 3b. So 1 is equal to negative 1 times b. So b is going to be negative 1. Okay. So what that means for us is that 1 over x minus 3x minus 2 is equal to, and we had a over x minus 3, so it's 1 over x minus 3. And then we had plus b over x minus 2, but we can just subtract it. And that way we don't have to make the individual 1 a negative. So minus 1 over x minus 2. And that's what we're looking for right there. So a few questions come up when we do this. First off, how do we know to use x equals 3 and then x equals 2? Well, we could look at the denominators. It's obvious that since this right here is what we have, if I plug in, after I do all that work and I arrive right here, if I plug in x equals 3, then one of them is going to cancel. In this case, it's a, and it's matched with that factor. If I plugged in 2, I would expect b to go away. So that's one way that we can do it when we have these linear factors. We could just plug in a value of x, but remember, just like we saw down there, we can only use it to solve for a single variable. If we use it again, the whole point of it was to get rid of the variable that we would be trying to solve for in that case. But there's actually an easier way to do this too, or at least a way that I prefer to do instead of this substitution for x. So let's go ahead and define the partial fractions first. All right, so when n of x divided by d of x is an improper fraction, meaning the degree of the numerator is greater, meaning the degree of the top is greater than the degree of the bottom. I should say greater than or equal to. Then we just use long division. So it's just like it is for numbers, for real numbers, we just have to use it on polynomials. So we would write n of x over d of x, numerator over denominator, is equal to some polynomial. Remember that we would have plus remainder over divisor. And the divisor is the same thing as the denominator in this case. So divided by a d of x. And I'm going to do a side note actually right here. And that is long division with polynomials instead of just real numbers. And so to do that, we're going to take, let's see, x cubed plus 2x squared minus x plus 5. And we want to divide it by x minus 1. Now, this division can be written the same way, like this. Just as a fraction. Or we could write it in terms of that division bar, x cubed plus 2x squared minus x plus 5, and then put that x minus 1 on the outside. Because that's actually what we're going to use. So to do that, put these off to the side, and we're going to go ahead and actually do the division. So remember, what we did before was we had 6 and 121, and we said, how many times does 6 go into 1? And it didn't. So how many times did 6 go into 12, really? And so really what that's asking is, what do we have to do to 6 to make it look like 12? We'd have to multiply it by something. And we're going to ask the same question. So what do I have to do to x minus 1 to make it look like x cubed plus 2x squared minus x plus 5? And we want to focus just on the first terms. Okay, so what do I have to do to x to make it look like x cubed? And the answer would be multiply it by x squared. So I'm going to put it over the x squared term. And then remember what we subtract. We subtract this times this. That times that. And so that would be x squared times x minus 1. That's x cubed minus x squared. So we want to keep it in order here. So we have x cubed minus x cubed. That would give us 0. And remember that we're subtracting the whole thing. So it would be 2x squared minus negative 2x squared. That's a double negative. So it's going to be plus 3x squared. And then we have a negative x minus something. That something is 0. So basically we're out of terms here. So what we do is just bring down the rest. Or if you want, we could just bring down the 1, just bring down that x. So I'm going to bring down just the x for now. So we want to know, what do we have to do to this x again to make it look like this, 3x squared? So we have to multiply by a 3, but we also have to multiply by an x. So that's 3x. You get rid of this 0 also. All right, so what do we want to do? We want to subtract x minus 1 times 3x. So that would be 3x squared minus 3x that we're subtracting. So 3x squareds cancel. And then we have negative x minus negative 3x. That's negative x plus 3x, so 2x. So now the question again, what do we have to do to x to make it look like 2x? And that would be multiply it by 2. And then we subtract 2 times x minus 1. That would be 2x minus 2. So the 2x cancels, and what didn't we do? We didn't bring down this 5, did we? So the 5 we should have brought down. It would go right here. And then we would have 5 minus negative 2. That's really 5 plus 2, that's 7. But notice we already have our constant term up here. And we're out of things to bring down, so that's going to be our remainder. So what that means is when we have this x cubed plus 2x squared minus x plus 5, and we divide it by x minus 1, we get x squared plus 3x plus 2 plus the remainder over whatever the divisor was, which was x minus 1. All right, so when we have the higher degree on top, that's what we have to do to try to make sure that we can actually go on and integrate after that, which we haven't even gotten to yet. All right, so when that's the case, then we want to write it like this. And remember, we're really talking about integration, so that's what we would have to do next. It's going to make integration pretty easy for us. So now we have another case. So the other case is when that actually doesn't happen. And this is similar to the one that we did a minute ago. All right, so we want to factor whatever it is that we have. And if our denominator is some power of a linear factor, meaning our denominator is p times x plus q raised to some power n, then we can write this as a sub 1 over px plus q plus a sub 2 over px plus q squared plus a sub 3 px plus q cubed, and that's going to keep happening until we get to whatever that nth factor was. So plus a sub 4, and these are just constants, all the a's. Px plus q to the n. So it's going to be this long summation. Okay, so if it's distinct factors, meaning we're multiplying them, then we would use this number 2 a bunch of times. So let's look at an example here. So this formula, the way that we write it, it actually looks, again, a lot scarier than it is. But this example should help it make sense. All right, so let's say that we want to integrate 5x squared plus 20x plus 6. And we're going to divide that by x cubed plus 2x squared plus x dx. All right, so the first thing we want